what we're doing, what are we doing? As you see here, see the picture here in the left corner. See, I'm using a special device to look at something. Well, I'm after light, of course, or my colleague here in the bottom right corner. And my other colleagues, again, they're manipulating some stuff there, but they're not looking at their optical bench. Yeah. Well, why is this? Simply because we are using, and most of the cases is infrared light, so we don't really see that light. But of course, you see cables, you see fibers. For sure, there is a kind of a laser, an optical source there, and for sure there is a photo detector somewhere. And what I can tell you that after the hard work is not to create this mess on the bench, but the hard work comes after we collect the signal. So after the photo detector, so that signal goes into a computer, and then we have to manipulate some data. And I can tell you that at least 50% of our time is actually spent on writing software, right? So about me, so after graduating, so I did physics, pure physics. So I've done a master in optics or optoelectronics and microwaves in France. Is there where we actually were kind of not fall in love, but I discovered that light can be used for medical purposes if you want. So I've done this in a Polytechnical Institute, my master, but then I moved back to the university, still in the same city of Grenoble, but is there where I left the title of the thesis here on purpose in French, but I'm quite sure that you understand what it's all about. It's about using optical methods, to investigate biological tissues. Yeah. Right. So about this technology, the OCT. So what that stands for? O is optical, because you're using an optical source that coherence as a property of light, and then we do some kind of tomography. So how does it work? Well, the thing is that what we have to do actually is to measure the time delay. So imagine that we have two objects, one after the other. Yeah. So what we are doing, we're measuring, what's the time delay between the light, back reflected or back scattered by those two objects. But because we are using light, we have problem. Light, travels kind of 1 million times faster than sound. And because of that, we have a little problem because we cannot really distinguish between these signals coming from two very close objects. So this is why we have to use some tricks. Well, and because of this problem, if you want, actually, these are actually created our jobs in the end, because we have something to do now. So we have to develop all this interferometer. So this is how every single OCT instrument is going to look like: optical source, a reference mirror, and sample arm, and then we have a decoder somewhere. And what's the beauty of the technology? Well, the beauty of the technology is the fact that whatever image we produce, we decouple the lateral resolution from the axial resolution. And because we do this decoupling, what does it mean? That means that actually my resolution, the images that I'm producing, do not depend on the optics. So that means that I can image objects by having an objective which is very far away from the object of interest. So this is why OCT is very popular, when used to image the back of the eye, yeah, because there I cannot do anything to improve the resolution. I cannot get any closer to the back of the eye, right? So now, if you look at this plot here to see where this technology is, so along the vertical, I've got the resolution that I can obtain in my images as a function of penetration depth and biological tissues. We are somewhere here, so we kind of filling this gap here, and it's a nice position to be in, simply because you see the ultrasound and the MRI, that's what's happening in clinic. Here we are in the lab, so OCT somewhere in between. So that creates, if you want, lots of opportunities for us, to talk to clinicians and so on. So that's a kind of image that we can produce with our instruments that we are developing. It's the one at the bottom here. So it's an image produced, if you want, that's in 10 milliseconds or so in vivo, in real time. Well, you see, that's a kind of, that shows somehow the progress in imaging the back of the eye. You see the image at the top, that was happening in 1850s, yeah, when people were drawing actually the back of the eye. That's the first OCT image produced in 1991 from in vitro. That wasn't in vivo and so on. You see the progress is absolutely huge. And of course, there are lots of applications of the technology. Most of them, of course, you see here the number of papers published over the years. Ophthalmology, of course, most of the papers are there, but there are some other lots of area of interest where all this technology can be used. We can, with OCT, can create not only images of the structures. Well, we can actually image, if you want, things which are moving. These are images of the blood vessels inside my eye. So it's images you cannot produce using any other technologies. And that's another application of OCT. And you can hear a sound. I hope that's also based on an OCT we built a few years ago, a stethoscope to listen to some flies. That's a Drosophila fly in its larval stage. So that's a creature which is as big as 200 or 300 micrometers in length. And what we are looking there is at the bottom there is the heart of that creature. But the beauty of the technology is that it allows to develop some other things like this beautiful stethoscope. Yeah, and then of course now we have some interest in getting small. So on the left here, that's the instrument that I built something like 15 years ago here at the University of Kent. That was about this size. This is a commercial instrument, and now what we want to do is to go small, is to use OCT via endoscopes and handhelds and so on. And why is that important? It's important because we can use this technology for instance for to guide surgery and so on. So we had projects where we tried to implement an OCT instrument via a medical robot and so on. And we did this kind of experiments again where in hospitals, when we looked at the larynx again, where the OCT was done via an optical fibers, inserted into the larynx of a patient and so on. And then that's again some other examples of things that I'm interested in doing. So what we see here, it's our images from the back of my eye, where the thing is that these images are from different axial positions. So it's like take a photo camera, take a picture, and instead of taking one in one plane, you are taking 100 images in one go, and you see them all at the same time. You can see behind one after the other. So that's one of the well, we put a lot of effort in this kind of technology at the moment, and that's another example. That's the lamina cribrosa. That's the part is the optic nerve, actually. Is that behind the optic nerve, just before going into the brain. Of course, I worked on imaging, if you want, or detecting some skin cancer, like this basal cell carcinoma cancer, and published a few papers several years ago. And also we use the technology, to figure out whether some embryos are alive or not. And that's pretty cool, because with our technology, we can assess whether an embryo is still alive or not, because otherwise there are basically no ways to telling whether that is okay or not. And of course, as I said, I'm interested in looking at how a biological object looks like, but also I'm interested at looking how it feels like. In particular, I'm interested at looking at the eyes, and figure out which are the biomechanical properties of the eye. And well, again, because this technology called OCE, optical coherence elastography, is based on OCT. Well, in the end, we are targeting exactly the same area, in terms of resolution and penetration depths. But of course, we can use this technology not only for the eye, and why it's important, because you can look at, can detect cancer and or some other things which are not normal in the tissue by using, because we are actually, as I said, we taking pictures of how the tissue feels like, right? And I'm going to be done in a second. So these are some other applications of the technology. So these are kind of the tissues that we can look at using this technology. And then the photoacoustic imaging, in the end, this is what I started to look into in the last few years. And what this is about, using the light produced by sound. How is this working? Well, now imagine like it's like you're having a balloon and you're blowing air into that balloon. The balloon increases in size, and at some point you stop. So then you release a little bit of air, and you're going to hopefully you're going to hear a kind of a squeak made by the balloon while contracting. This is what's happening. Now we have a cell. We're shooting light at that cell. The shell is going to increase in size, and then we stop our source of light. Yeah. So the source of we are cutting off the laser. the result, what is going to happen afterwards, the cell is going to reduce its size and make a noise. So we're after that noise, and this way we can measure where that noise is coming from. So if you want, in the end, what we produce is an image of the sound produced by the tissue. And of course, we have some other different directions of research. All of them derived from OCT, if you want. But of course, if you want to learn more about this, please go on this website. This is only for my knowledge, because all the work this is done in collaboration with my colleagues. I cannot do anything for this alone. Yeah. So, but you can find on this website, you can find everything about our research. Yeah. Okay. Thanks. I think I went well. 15 minutes. Okay. I'm good. I'm happy.
No worries. That was great. Thank you.
Okay.
So next we are going to have Professor Burchell give us a talk.
Right, so welcome. This is Professor Burchell here. I'm just trying to share my screen. There we are. And in theory, I can now start the slideshow. Except my laptop is very slow. It thinks it started the slideshow. Ah, there we go. So hopefully people can see things. Yep. Right. So welcome. I'm Professor Mark Burchell, and I've got my 12 minutes. So I'm in the Centre for Astrophysics and Planetary Sciences, and we've got two logos, a nice old one and a sort of new one. But at the University of Kent, for a long time, we study solar system impacts. You might wonder how universities choose their areas of research, but Kent was opened in 1965, and one of the first staff was then lecturer that became the first professor of space science, Tony McDonnell, who specialized in working with NASA on dust in space. And you meet dust in space because you collide with it at very high speed. And so we became a group that specialized in solar system impacts. Meanwhile, my brief history was I was a physicist. I was at Birmingham, graduated, and in those days, about 4 decades ago, shall we say, they only had one degree, which was physics, and you picked a pathway through it. And you had to have a major and a minor pathway. So I specialized in theoretical physics, and then the subspecialty was astronomy. And then did a PhD at Imperial in experimental particle physics, and was then a postdoc at Imperial, which meant you went backwards and forwards from Imperial to CERN and backwards and forwards every few months to do the experiments at CERN. And while I was at CERN, I told people, I want a job. I want to go to America. So one morning at breakfast, I was interviewed by some Americans and took a postdoc position, which is, as I say, what you do after your PhD before you get a permanent job. You take these fixed term things called postdocs. And I got this job, a place called Santa Cruz. And everyone was congratulating me a few weeks later. And someone said, well, what's it like? I said, well, what's what like? Santa Cruz. I said, well, I don't know where it is. So before they invented the World Wide Web, you had to go to a library or a bookshop and pretend to buy a book about travel guides to California to find out where you just accepted this job. And if you want to know why the World Wide Web hadn't been invented yet, because I used to go to lunch with this guy called Tim who was busy inventing it. Because CERN used to do it, but no one knew he was doing it. It was just this guy who saw it at lunch. So anyway, I then spent 3 years as a particle physicist in California, then went back to CERN as what's called a CERN fellow, working at the CERN laboratory in Geneva for 3 years. And did something unusual in that I got my faculty position in a totally different subject, which was space science at Kent. Nothing to do with particle physics or theoretical physics, but it was a growing field, and there's a mismatch when fields grow between the supply of trained people and the number they need. So they hired me, which was good for me, and it clearly didn't go wrong, so I'm now a professor. So I think we can all congratulate ourselves on that choice and feel good about it. But these things do happen occasionally. You have these sliding door moments when you step out of years of being a particle physicist, going to exciting places like CERN and California, and then you join a group at Kent which works with exciting people like NASA and the European Space Agency. So it was win-win. What we do is we keep banging the rocks together, a classical allusion to a novel. You've got to work out which one, I'm afraid, but in the solar system, things move very fast under the influence of gravity, and they collide with each other. It's one of the most natural things that happens. It's how the planetesimals accreted mass. They bumped into each other. Then occasionally they bump into bigger things, and we end up with a small number of large planets plus some leftover rocks, plus in the outer solar system, the gas giants. And the impact speeds of 5, 10, 20 kilometers a second. And if you watch the landing during the week, you'll notice that the spacecraft was entering the Martian atmosphere at over 5 kilometers a second and had to rapidly shed speed during its descent. But if there's no atmosphere, and if there'd been no parachutes or anything like that, it would have gone bang into the surface and left a crater. These are natural events on solar system scales, but here on Earth, they're not natural. These speeds are not natural, and the pressures you get, hundreds of gigapascals, hundreds of tens of megapascals probably are strengths of things. Hundreds of gigapascals are abnormal. So it's not natural, and we need special tools to explore this and understand the phenomena. And that's what we do in our lab. And before we show you that, for those who are impact specialists, this is the moon, and this is a new crater. Craters are still occurring. There was a lunar reconnaissance orbiter that was going around. It takes some photographs, go around, it visits the, oh, wait a minute, there's a new crater there. So craters are still occurring on solar system bodies. We've not quite seen that one. It was between images. Here's one on Earth, 60,000 years old. You've got your favorite crater on Earth if you're in this sort of field. That's in Arizona, and it's only about a kilometer or so across. But craters are just craters. Those are when big things hit. When small things hit, they hit your spacecraft, that can also leave a hole and be a problem. So we study it to understand the evolution of solar system bodies, and we study it to try and understand the risks to space vehicles and things like that from the smaller dust. Fortunately, there's a saying that big is rare, that there aren't many big things hitting us. There's lots and lots of small things all the time. So to do this, we've got a gun in our lab. There's a terrible photograph at the bottom, but it's about a 5 meter long gun, which can fire at the right sort of speeds, 5, 6, 7 kilometers a second. And if this works, I know we're on YouTube, but for a minute, maybe even less, if it will start, I will show you, you can visit our gun lab where, right, we'll accept the cookies, I think, but that's a better picture of our gun lab. That was my postdoc, Catherine. And if you do want to go and look at this, you can have a tour of our gun lab, and it will actually work in 3D as well. Well, no, I don't want to sign into YouTube. We're already on YouTube. But you can, if you're wearing goggles, watch this in 3D. But it's got stirring music as well. But it explains how the gun fires from one end down to the other end.
I'm not sure the link is working.
Right, okay, we'll skip that, but we'll just go on then. I can see it on mine, but I guess it's not clear on anyone else's, so just got to get back now to this. So if you want there, I'm sure we can find the link afterwards and you can watch it. But what we do is we use that gun and fire small projectiles. Some people have larger guns, can fire slightly larger ones, but that's, I'm afraid, bit hazardous, and one thing we're not allowed to do is fire really large things which might destroy cities. For health and safety reasons, that's not permitted. But what we do is we test materials for impact damage. So space vehicles have to be tested to make sure that you don't puncture, for example, a crew habitation quarter, or that you just puncture a standard satellite and damage the interior. We also do the opposite, because if we can collect those small particles in space at very high speeds, we can bring them back to Earth and study them and work out what everything is made of in the solar system, grain by grain. We also design new detectors so that we can work out how much dust is in space deliberately by having hits, basically. We just sometimes, the simple ones, just count the number of holes. You bring things back, oh, there's a crater, crater, crater. You count them up, then you look inside them at scanning electron microscopes to see what everything's made of. And there are better techniques as well, but we won't go into those. We try to understand the physics of the underlying processes. We do something called astrobiology, which is getting to this sort of odd end of things, but you must have seen the late night bad science fiction movie when the rock comes from space, something crawls out, scuttles away, we're all in danger. Usually starring David Duchovny or someone like that, but But if you do watch these, the problem is when these rocks come from space, they arrive at high speed and smash into things, and the shock would probably kill things. But we study to see at the wild end, does anything live, but also what happens to amino acids and things like that, which are probably more prevalent. Do they get synthesized into more interesting compounds, or do they just break apart? So even amino acids may or may not survive. So there's all sorts of fun trying to understand how organic materials arrive at planets from space. And one referee wrote a rather scathing, he passed the paper. You send your papers to journals, referees like markers of your exam papers, sort of, oh, well, we'll let you publish that, but you've got to change this, this, and this. One of them let us publish our paper, but accused us of doing experiments which are obviously fun. Well, okay, so let's look at some experiments. We worked with ESA in the last 18 months, something called the Deep Space Gateway, which is a proposal to put a space station next to the moon. NASA has signed contracts with Falcon 9 to launch the first components in 2024. And what we're proposing is they should put a dust detector on the outside. We don't know if ESA's going to yet, they're thinking about it. But it's got lots of things that will measure the dust at 1 AU, the distance from the sun is 1 astronomical unit, but not in low Earth orbit, it will do it in lunar orbit, whereas at the moment there's no human materials, human products. So we can compare Earth orbit to lunar orbit. We can try and look at asteroidal versus cometary dust. We can try to look at interstellar dust. People may remember there was controversy or big excitement maybe 18 months, 2 years ago, when a big object came from interplanetary space through the solar system. Well, so does small bits of dust. We can collect that dust. We can try and measure the organic content of dust grains. And there's other things as well, where a bit of background science where we just do day-to-day measurements as well as the exciting stuff. We proposed that to ESA. We've tested things in the lab and we're waiting to see if they will agree. And we've got partners in Germany, France, Italy, and European industry is all lined up behind us. So these projects require industry to build, a space agency to launch, and scientists to do the work. Another one, we'll see if this video works. So you have to tell me whether this one's worked. Take an innocent target and you do that to it. That's a video of what happens if we put a block of ice. You think, why ice? Well, think of a whole ice world out in the outer solar system, the icy satellite or one of the outer planets. It's covered with ice. If you hit things hard enough, you don't just get a crater, you can blow the whole thing apart. This one was actually an ice shell, but we've been exploring solid ice targets filled with water, ice targets that are hollow, ice targets with a rocky core and a water layer and an ice surface, which is what some of the places like Europa and Enceladus are held to be. So we do things like that, and that was the one where the referee said they're obviously enjoying themselves doing their experiments. But the paper did get published. And we try and work out at laboratory scales how much energy per kilogram of target you need to blow the target apart. Then you have to scale, as I say, to solar system sizes, because you're not allowed to do these things for real. So we do have to extrapolate the results to the real solar system. Then the exciting one is you can fly past icy ocean worlds. There are some worlds, as I say, not just blow them apart in our models, but some of them actually spray water into space. And this, if I can find down here is the cursor, these are plumes of water coming off Europa. So if you flew a spacecraft through, you'd be sampling the interior ocean of Europa. Now, most of what it's going to contain is salt. So as a PhD student has been seeing, can we tell salts? Because there's more than one type of salt, not just NaCl. Then what happens if there's organics frozen in there? So James knew another PhD student who's now a postdoc at Berkeley. He's been flying backwards and forwards across the Atlantic before shutdown. And so we've published one paper already, and they're working on more to see what type of organics. So if there was organic-rich ocean, which is a step towards life, surely. And then what about, suppose there was life, would it be sprayed out? Well, think tardigrades. For those of you who know about tardigrades, they're hardy tardies. You can suspend them, you can freeze them, and they live, and then defrost them again. And so we froze some, put them in our gun. This is one before, and this one is afterwards. It did crawl away afterwards. And we looked at survival rate against shock pressure. And it was 100%, and then it falls at about 1 gigapascal, and they sort of, half of them, 2/3 die, and then they're all dead. At this stage, you're getting fragments, I'm afraid. These are 1/10 of a millimeter in length, so they're very small. In theory, if they were the sort of life that was there, you could spray them into space. But actually, they're freshwater creatures, so they wouldn't like the brine. But, it's just an example. I thought, if you're flying or in orbit around Europa, what sort of shock pressures would you get versus altitude of the orbit? Tardigrade survival down here, Europa, flyby shock pressures, no good. If you go to Enceladus around Saturn and it's spraying life into space, well, we say you might find it. And that's coming soon, hopefully, in the journal called Astrobiology. Alejandra, my master's student, and myself were the authors on that one. So summary, we study impacts. They're not natural to us, but they are the most natural of phenomena in the solar system. Space debris is a big news story because we're littering space, I'm afraid, with bits of debris, bits of spacecraft. People worried for decades if we pollute Earth's orbit too much, you can't access it anymore. When we go to the moon, we might be doing the same, so we want to monitor that. And you can think of all the great things you can explore in the solar system via impact phenomena. And it's a long list, it's been going for decades, and it will keep on going for decades. The research is mostly funded by something called STFC in the UK. I've got lots of related staff and research students. I've had 5 of these postdocs myself over the years, 15 PhD students, and about 14 masters by research students. And so they're now all around the country and the world doing various jobs. Some are school teachers, some work at aerospace companies, and some still work in universities. So that's the end of my talk. And I'll finish that and I can stop sharing my screen, hopefully right on time.
Great, thank you so much. Hope everyone enjoyed our second talk. And now we'll go swiftly on to our third talk by Dr. Ramos.
Hello, let me see if I can now share my screen. Let's see. Okay, hopefully that is working for everybody.
Yep, perfect.
So, I'm Silvia Ramos. I'm a senior lecturer in the School of Physical Sciences here at Kent, and I specialize in materials physics. I'm part of this group called the Physics of Quantum Materials. And let me tell you that I thought this type of talk was actually really interesting because it gives us the opportunity to show you a bit of science, but also a bit of the scientist side of things. Science is something that we do very objectively. It has to be reproducible. It doesn't depend on who is doing it. And sometimes we forget that actually that for science to happen, you need scientists to be there. And it's a way of working and of living that might not be entirely obvious to everybody. So I thought this was a very good opportunity to have a little bit of both. So let me show you where I started. So this is where I started. This is a photograph on the left of the University of Salamanca in Spain, which is where I was born and I grew up and I went to university. That's a very old building because it's an old city that has an old university. And I studied physics there, as you might have guessed from the picture on the right, because they had a massive pendulum in the middle of the atrium in this building. So that is where all this started. I studied physics there. And let's see, this is where I am now. I'm again in a small historical city, very beautiful, and also in a physics department. Now, I guess if I convince them to install a massive pendulum somewhere, I will have closed the loop, okay? So what I'm going to be talking about now is what happened in between, okay, these two things. So the first thing that happened was that I decided to go and finish my degree somewhere else. And I went to Bristol for my final year undergraduate, and I loved it there, and they liked me too, so they offered me a PhD position, so I stayed a fair number of years in Bristol. And the European Union kindly agreed to pay for both of them, so, you know, I'm quite grateful to them. So I spent there about 4 years. The last 3 and a bit was writing my thesis, and as you can see in that cartoon there, it was indeed written in blood and sweat, and tears and coffee, and I loved every minute of it. So I decided to stay in science because it was a great experience. While I was there, I was working on, well, let me show you this next slide so that you get a bit of a summary. I was working on the structure of materials and how you relate the structure to the properties of a material. That has been the common theme of my research career. So electrons and atoms, and why is it so important? Well, because they can make a massive difference. If you look at the right-hand side picture, you have graphite on the very right-hand side. Next to diamond, they are both carbon, but all that is different between them is the way those atoms are arranged, and their properties are very different. So atomic structure is a big thing that determines the properties of the materials that we are going to be looking at. And if you think about the electrons, you're looking again at how they arrange themselves, how they get organized, and how that has a massive effect on the properties of the materials that you are looking at. So for magnetism, you can have disordered states, and then you cool that material down and they order, and suddenly you have a magnet. Okay, or for superconductivity, you could have absolutely random and correlated electrons doing their own thing, but you cool them down and suddenly you have them nicely paired and doing this coherent dance across the material with no resistivity. So I thought that was really intriguing, and how you correlate the structure and the properties of the materials is what has been driving my research all of these years. Now, when you look at these things, you want to be able to actually look inside the materials to be able to correlate this structure and the properties. Mostly because anybody that has eaten an orange knows that actually the outside and the inside of something don't necessarily do the same thing. Okay, so looking inside is a very important, very valuable tool when you study the properties of new materials. Of course, there are ways of doing this. I mean, you could take a hammer to thing and break it, and then suddenly that was something that was in the inside is in the outside, and you can study that. But I tend to study with new materials, things that my colleagues that produced the sample worked really hard at making. And if they can spend a couple of years producing a new material with nice crystals so I can go and look at them, they wouldn't like me very much to take a hammer to them, okay? I would lose friends very quickly if I destroyed somebody's work for the last 2 years doing that. So I don't do that. I like my friends, and it's good to have collaborators. So what I do is I take these samples, these new materials, to try to understand what they are doing and how that relates to the structure to these places called large facilities. Large facilities are labs that are shared tools, okay? So you get these big machines that will produce loads of X-rays or loads of neutrons, loads of neurons. All of these things are things that you use to look inside a material. And you build these big buildings and produce a lot of these that are then shared between different types of instrumentations. You can do very different types of experiments in these places, and scientists from everywhere go to work and do measurements in these and experiments in these places. So I have worked mostly in 2 of them. One of them is actually in Grenoble, which is the second time that appears today. I realized in France, that's the European synchrotron, and they also have a big neutron source there called the ESRF and the ILO. So that is in France, and after Bristol, that's where I went to work. I worked at that big ring-shaped building for a few years as a postdoc. And they're extremely exciting places because such different science happens there. So you're there doing your own things and your own interests, and you meet loads of people working on similar problems that you can discuss and learn science from. And they change constantly because they are shared facilities. So you go for a few days and then you go away. So when you work there and you're constantly there, you see all of this science that's happening in front of you, which is great. So I spent there almost 3 years, and then I came back to the UK, to the University of Birmingham, to do another postdoc where I was again working on the properties of materials using these large facilities, but this time working at the university and then going and using the facilities when I needed to, so traveling backwards and forwards. And from there, I moved to the Rutherford Lab in Oxfordshire, where they have another 2 of these coupled types of buildings. So you can see on the left-hand side, another ring-shaped building. That's another synchrotron, that's the X-ray place, and that's where I used to work. But I also used the neutrons and muon probes that are found on the building that has the blue sites on that same picture. So they are very likely places to work. and to go and do experiments. And from there, I moved to Canterbury. So that has been the path that I have followed during my career. Now, researchers come in all sizes and flavors and types, and different things are the driving force for different people. In my case, it's always been curiosity. I've done very different things. So I've done some technique developments when I've been working at facilities. So I built a beamline while I was at Diamond. I arrived at the place where the synchrotron in the UK when they were building it. So I was part of the team that built one of those instruments. And I've also worked on things that have no applicability whatsoever, but were extremely good fun to work on. So for example, that is this spin density wave that I have there as part of the publications that have been happening. At the moment, I'm doing a lot of work, in fact, on battery materials, so energy materials. But the driving thing behind all the work that I have done has always been, can it be done? And why? Okay, so different people will have different questions that keeps them going every day, and those are mine. Can it be done and why? Okay, so yeah. Now, quick summary. So what have I learned? So I've learned physics, quite a lot of it over the years, but always with a strong awareness that there is actually a lot that I still don't know. And that comes with about 30 seconds of being really overwhelmed and thinking, oh, this is never ending. Followed by another good few minutes of thinking, isn't that great? Because I love learning physics. And there's still loads that I don't know. So there is a lot that I can still do. And that is wonderful. The second thing that I've learned over the years is that I really don't like moving houses. It's awful. It doesn't matter how many times you do it. It's still a lot of work and very stressful. But it's part of the job of a scientist these days. So you move a lot because you learn different things from different people. So you just have to accept that is the case. I've worked at universities and large facilities several times, on and off. One of the things that I have learned about myself more than anything else is that in fact I do miss teaching when I'm working at a large facility. So they are great places because you see all of this science happening. But you don't get to teach the fundamentals, the physics that you learn when you are at university, and I miss that. I find that enjoyable, and I think it's good for my way of thinking about physics problems to have that responsibility of communicating these fundamental aspects of physics to people that are learning them. So that's one of the things I've learned about myself. The final one is that you can never be bored when you work in large facilities. So I don't work there permanently now, but I go to do my experiments on a regular basis, and they're great. So it's high adrenaline because you always raise the clock when you're doing experiments there. They give you a few days and that's it. You have a couple of days, 24 hours a day. It could be a weekend. And you have this time for you, and you just have to do this experiment that you've been preparing for 6 months. So, you know, that is not for everybody, but I love it. It requires lots of coffee, so hence my coffee machine picture there. It's also work that you do as part of a team. And I've met some amazing people there, and they are definitely not boring. I mean, these places are complicated, and you do work with very little sleep during that time, and having people working with you from whom you can learn and that you enjoy working with is a big part of it. And I've had a great time doing that sort of thing. Also, the equipment is unbelievable. You use these massive instruments, really complicated, to do these experiments, and you make them do exactly what you want, and that is extremely satisfying. So that is definitely a plus and something that you can never be bored. What can I say? Until you've seen a 7 Tesla magnet quench and produce these masses of liquid helium becoming a gas and bursting all the pressure disk around the place, you haven't lived. And I've seen that a few times. That's one of the pictures that we have on the right-hand side. When you've seen it 3 times, you actually go away and get your camera because it's quite impressive. So that is all I wanted to talk about today. I'll happily answer questions once we finish all of that. Okay, thanks.
Great. Thank you so much. Great. We're on to our fourth talk of the late afternoon, evening. And next we have Dr. Carr.
Hello, can you see and hear me?
Yes. Yep. I can see your presentation and hear you.
Oh, wonderful. Yes, I'm Dr. Carr, and I'm going to talk about condensed matter theory. And I thought actually for this presentation, rather than concentrating on what I'd do, I just wanted to give you an overview of the topic, because it's often seen as the poor cousin to high energy or particle theory, because nobody really knows what it is outside those who do it. So I hoped to get you as excited about it as I am, and I'm at the University of Kent in the Physics of Quantum Materials group. But like everybody else, I just wanted to emphasize that academics were students once too, and so how did we get to this stage? So at least in my case, my undergrad was in Oxford. I then stayed in Oxford for a DPhil, not because I wanted to go off and explore elsewhere, but actually I got a really good offer from a supervisor there. And when I went to interviews in other places, they heard that I had this opportunity to work with Alexei Strelich in Oxford, and they said, well, you'd be stupid to come here then, wouldn't you? So I kind of stayed in Oxford, but as luck would have it, my supervisor, in fact, then moved during my first year. So I didn't stay in Oxford at all. I got the supervisor I wanted, and I got to explore the world. My supervisor moved to Brookhaven National Lab, which is on Long Island in the US. So I actually spent 3 years of my PhD there. I then did postdocs in Trieste in Italy in the International Center for Theoretical Physics. I'm in Birmingham, and in Karlsruhe in Germany, in the Black Forest region. So again, there was plenty of opportunity for travel. One of the great things about an academic career, I think. And since 2013, I've been a lecturer at the School of Physical Sciences in the University of Kent, which you are all virtually visiting just now. Such a pity you couldn't actually be here. It's a lovely city. So, I do theoretical condensed matter physics, and more specifically, I work on strongly correlated systems. And given that I'm in a group that says quantum materials, I just wanted to give you a glossary of what each of these terms means. So the first term, condensed matter, I mean, people argue a little bit about exactly what it is, but most people, and the core of it is just materials. So I study materials and their properties. Quantum materials is just, I'm studying mostly the electrons in it, so quantum properties, and even the most basic things of condensed matter like Ohm's law actually come from some quantum physics. So quantum could mean almost anything in this respect. And then strongly correlated, what I'm going to try and show you by the end is exactly what that means, but roughly speaking, it means the system is more than the sum of its parts, but we'll get to that by the end. So starting at the beginning, if I'm studying a material as a theoretical physicist, how do I model it? Okay, and the difficulty is there's a lot of stuff in the material. Avogadro's number is very big, so typically I have to consider about of the order of 10 to the 23 electrons. And so how can I possibly, as a theoretical physicist, as a mathematical physicist, model so many things? That's a lot of equations. So there's complexity involved here. So the first solution is I could use a really big computer. Now, big computers cannot get anywhere close to 10 to the 23 particles, but you can get big enough that you might call it sort of macroscopic. You can look at classical motion, you can look at quantum systems. There's many methods to look at these. And the wonderful thing about some of this is you really directly treat the many body system, so the system with all of the electrons and atoms in its full glory. And if you want to do realistic modeling of a real material and make real predictions about that, then usually you have to go to this sort of thing, at least partially. But unfortunately, if you go for this ab initio method, the approximations you have to use to make it tractable at all fail for the most interesting materials, okay? And in fact, strongly correlated systems you could define as those where you can't do this for. Now, that's not to say these are the only useful materials, but there's certainly a large class of materials where you might want to think, what else can we do? So the other thing, which is what I do, is I use a pen and a paper. So I play with toy models, I play with quantum field theory. So in fact, the methods I use are exactly the same as are used in high energy physics, of Feynman diagrams, of all sorts of other methods of quantum field theory, even methods of string theory find applications in nanowires. But the point is, I'm writing equations down. How can this possibly be useful to model the original material I started with in its full complexity? And the answer is, it only can if I ask the right questions. I can't answer everything like this, but if I ask the right questions, I can. And the key concept here is the idea of universality, which won Ken Wilson the Nobel Prize in 1982. And this is again based on ideas of renormalization, which were borrowed from high energy physics. They used in a slightly different way in condensed matter, but it's all the same maths that we use. But I mean, there's a wonderful book by Volovic called The Universe in a Helium Droplet. So basically everything you can see in the universe, you find the same physics in helium in its different phases. Lovely ideas there. But the idea of universality, things that some things don't matter about all these details, mean you can slim down your model to something that hopefully is analytically tractable. So as a example of this, you can ask a question, what's the phase diagram of a substance? So here's like something, typical substance, for example, water, there's solid, there's gas and liquid. But let's just draw it in a slightly different way. Okay, so hopefully those of you who are undergraduate who have taken a thermal physics course recently have seen pictures like this. So I'm drawing it as a function of density at different temperatures. Okay, so if you're beyond the critical point at a temperature greater than the critical point, you vary the pressure, density varies continuously. Exactly at the critical point, there's an inflection point, and below the critical temperature, you can go from a gas to a liquid. And when you do that, there's a first order phase transition. So there's a jump in the density as you go through this. And where this jumps happens, the different densities gives something called a coexistence curve. And you may think, well, understanding this depends on all the details of the material. Okay, think again. Here's a plot of the coexistence curve. I've scaled it as theoretical physicists want to do in what I call dimensionless units. So the density divided by the critical density and the temperature gets the critical temperature, and all this data falls on a nice line. The crucial point in this plot is this is not data from one material. This is data from 8 different liquids and gases, ranging from noble gases to oxygen gas to CH4. So they all fall on the same line. So obviously details of the gas are not mattering here. So if I ask a question, what is the critical temperature? That's difficult to predict. It's not something that's universal. I'm not going to be able to answer that with my analytical methods, or at least if I do, you should look at me and say, well, I'm going to measure it. That's not going to be right. And it never will be. However, there's other questions which you can ask me, such as the shape of this curve, if I scale it correctly, and that I might be able to predict exactly, okay? And this is what Wilson argued in this idea of universality, and this is one of the central features why these seemingly toy analytic calculations that you might even be doing as an undergraduate in your first condensed matter physics course, and you think, well, this seems too simplified, how can this apply to a real material? Actually, it does, but so long as you're asking the right questions. So just as an example, I wanted to put this in because it shows a few lovely things about Kent. In particular, the School of Physical Sciences has not just physicists in, but also chemists, okay? And my background is mathematical physics. I never really went near chemists before because they deal with dirty stuff and things which tend to break when I'm close to them. But I was speaking to them because we're in the same department, and I'm interested in magnetism from a mathematical point of view, and they're interested in mathematical magnetism from the point of view of making things and measuring the magnetic stuff. And they showed me data from this material. So this is, I can't even pronounce the name of it, okay? It's absolutely horrible thing with the loot is, I think, lutamine. It's an organic compound. The unit cell has about 30, 40 atoms in it. It's absolutely horrible. It's got some crystal structure. They draw it for me. I look at that, I say, how am I going to make an equation that governs that? And then they say, well, we've measured the susceptibility, magnetic susceptibility as a function of temperature. Can you help us analyze it? So we think about it, that the magnetism comes from the copper atoms, and you can't see it from this picture, but speaking to the chemists and the people who actually look at these structures, the copper atoms form bilayers. Now, the coupling between the bilayers is the strongest one. So actually what you can then do is say, suppose that's the only coupling there is. So basically there's a copper atom at the top bilayer and a copper atom at the bottom bilayer. So you've got two atoms. Out of this horrible mess, I've got two atoms. I can solve that. I can write down equations for it. And then I can say, okay, well, there's some other interactions there. Let's treat them perturbatively with something like mean field theory. And you get an equation, a very simple equation. And of course, I can't say exactly where this peak will be. That will depend on the value of the coupling. But if I fit to it, I get an equation. The equation is there. And that's this green line here, which goes ridiculously well through the data. Okay, so from something so complicated, the only thing that actually matters for susceptibility is this one coupling between bilayers. And that's pretty cool. Okay, and that's why analytical work is still useful. It's also why it's really useful to speak to people who do different things than you, because there's no way on earth I could ever have made this compound nor measure any properties of it if somebody gave it to me. Whereas the chemists think what I've done to get this formula is black magic. And so it's wonderful that this calculation that is, I mean, from my mathematical background, is ridiculously trivial, is actually so useful for other things. I realize now I'm running out of time, so I'm going to have to skip through a couple of stuff. Let me just mention at the end my main research areas, in case you wanted to ask anything about them. But it's all based on this idea of toy models, simplified models, looking at new phases of matter. And so long as you're asking questions about generalities of them or universal properties, then these are still applicable to real materials. So I look at Ohm's law, which is not as simple as you ever thought it was. Anyone who said Ohm's law was simple is lying. And that can be applied to quantum wires. I look at topological phases, and I've got a nice interest in quantum impurity models as well, which if you're interested in any of these graphs, ask me what they are afterwards. Each of them I could probably go on for an hour about, but I won't. Thank you, Molly.
Great, thank you so much. And yeah, let's move on to our last talk of this Speed Science event before we open it up for questions for all of the wonderful academics. So we have Dr. Kinnear closing us out.
Hello. Right here, just sharing the screen. I'm going to do that as well. So hopefully if I play videos, it's going to work okay. Right, okay, so my name is Dr. Kinnear. I didn't put together any slides on my sort of path through things, which I think has been a fairly common thread that people have used. So I did my bachelor's in science at University of Warwick, which was followed by a research master's with Professor Boris Gansig at the same, also University of Warwick. After that, I came here to Kent for my PhD and didn't leave. So I did my PhD and then did what is sort of teaching postdoc thing afterwards, followed by the lectureship that I currently have. So I don't actually have any current research as such. I'm primarily employed as a teaching academic, but I do research things across a variety of different purposes just because I find them fun. But I'm not leading any research as such. So I decided to talk about what I did over the course of my PhD, and it's the area that I've continued to have some involvement with, but isn't I'm not sort of actively researching it. So my PhD was investigation into triggered star formation by radiator-driven implosion. And I'll go through what those different bits are and how I went about what became a complete PhD, which took possibly a little longer than intended. I got very caught up in the actual teaching element a little earlier than I should have and drew it out just a little bit, a little tiny bit. So in space, you have these regions called H2 regions, and they more or less have this kind of structure. So you have some hot star or collection of hot stars, so O stars or OB associations. And when those stars form, they have very harsh radiation fields with substantial contributions to the radiation field well beyond 13.6 electron volts. And 13.6 electron volts is important because it dissociates atomic hydrogen. So if you have atomic hydrogen with its little electron going around it or not going around it, as the case may more technically be, it manages to strip the electron away. And any excess energy beyond that contributes to the overall kinetic energy of the system, the overall thermal energy. So you have this front expand out from this formed star. And it goes in kind of two layers. You have an initial layer which breaks down molecular hydrogen into atomic hydrogen. That's this dissociation front. And that you have this region of atomic hydrogen. And behind that, you have this ionization front. And the ionization front gradually expands out based on the rate at which it can ionize hydrogen compared to the recombination rate, where hydrogen is recombining and needs to be reionized by an extra photon. And eventually you'll reach this Stromgren radius, whereby your ionization rate matches your recombination rate, and the front can't proceed any further. But while this front is expanding, it's expanding through material that's not yet been interacted with this harsh radiation field. And these things are not completely uniform. The idea of the Stromgren radius is a completely uniform cloud. In practice, you have lumpy bits to it. It's not all homogeneous. You have these varying densities. And you can have these blocks that are higher density than the surrounding. And when the ionization field tries to expand through that, it doesn't get as far through it in the same time that it goes through the less dense gas around it. And what you have is you have this very dense center, which the upper layer of is being ionized, and you're getting recombination. And the recombinations and ionization events are producing a whole bunch of radiation at 13.6 electron volts. And you get these very bright rims in that 13.6 electron volt band, where you can see where all of this recombination is happening. And these are some pictures of such locations. Some of these will be familiar if you're familiar with space things. This is the Eagle Nebula, a very well-known picture. The overall center of this thing is one of these H2 regions. And you can see that this is not a sphere. It's a weird, lumpy, weird shape, which looks like an eagle, apparently, allegedly. Whoever named it thought it looked like an eagle. And you get these weird shapes. It's not a uniform expansion. And because of these weird shapes, this is a close-up of the Eagle Nebula portion here, called the Pillars of Creation. And this is kind of on its side relative to this image here. This is a very lovely high-resolution picture. I've noted that most of these are from Hubble Heritage Team. You can see what's going on. So these bright edges around these clouds are where you're getting this recombination. There's dense gas inside, which is opaque to some of this emission. And all of this area around it is this hot ionized gas. And you can see it has little twiddly bits. And one of the very interesting things about this image is some of the little twiddly bits change between when these images are taken on the span of things like decades. And on distant scales like this, these things are like light years in size. That's very fast. Things are happening here that are very fast. This is another lovely picture. This is the Carina Nebula. And similarly, you can see these kind of outlined clouds. This one is also from the Carina Nebula, and you see this little feature here. This is what's thought to be a bipolar jet. So from a forming star, you're getting these jets of material thrown out, and those are going out there. And in fact, it's just here in the Eagle Nebula picture. If you look, this Eagle Nebula picture was taken in 2015. There's a 2005 picture where you can see that this little jet has moved position. And on these scales, that's very, 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 very fast. So what that means is that some of these things, you can see probably one there as well, have stars forming near the tips of these objects. And that may not be coincidence. And so one of the concepts that was brought into play was this idea of triggered star formation. So lots of stars will form just because there's enough gas that it collapses down into a high enough density that you start to get hydrogen fusion, blah, blah, blah. It gets a bit more complex for massive stars because no one understands how they work really. Generally, there's this idea that you can have external factors contributing, so bumping up this probability that you'll be able to form a star regardless of how much material you have. And there are several different sources for these. So there could just be stellar winds, driven turbulent motion. Turbulence in space is a bit weird. It's not very well understood, but there's definitely turbulent motion there. It's not quite clear what drives all of it. Supernovae. In fact, there was a paper that suggests that there's a slight possibility based on certain types of astronomical record that the sun may have been formed via triggered star formation led by a supernova. I don't know how well accepted that is. I think it was just more of a concept. And radiation. So the ones that I was looking at with this, the radiative-driven element of radiative-driven implosion, stem from this idea of radiation, which is Ropeff and Bertoldi. The idea behind this is that you start off with this expanding ionization front. None of this is to scale. And you have this gray sphere here is our dense blob of gas. The ionization front expands to nearby. Once it hits the surface of this, what you get is that the inside of this ionization region is of the order of 10,000 Kelvin. There's basically an equilibrium point where oxygen recombination from collisional excitation is giving up enough radiation that just leaves the system that its temperature kind of flattens out at 10,000 Kelvin. But inside this little gray circle is about 100 Kelvin. So this red line, you have this boundary between 100 Kelvin and 10,000 Kelvin, but they're about the same pressure and density because it's the upper surface of this gray cloud that's been ionized. And what this means is you have this hydraulic leap. You have a sudden jump in effective pressure. So the density here and on the surface is the same, but the temperature is orders of magnitude different. Now, what this means is whenever you have a hydraulic leap, you'll start generating a shock front. So as the ionization front goes around and encompasses the entire object, it doesn't have to be a sphere, it can be longer as well, you get this surface that's been ionized acting as a source for a shock front that's driven inwards, perpendicular, normal to the surface of the cloud. That shock front will drive inwards, and potentially it'll drive densities to a point where you can get triggered star formation. Maybe. The reliability of this theory is questionable. The observational evidence is difficult to obtain, and there are various pieces of research going on into can we actually say from observational evidence that we think this is happening. I looked at the theoretical side. Can we construct a theoretical scenario where we can make it happen? Because if we construct a theoretical scenario where we can make it happen, and it's been shown that it can happen, this wasn't the first simulations to do this, but it shows under certain circumstances. So I will not spend very long on these at all because that's not ideal for a 12-minute presentation, but more or less my thesis involved using these equations in a numerical model. So we had a large-scale computational fluid dynamics model. It made use of basically these equations to define how the fluid making up these clouds of gas behaved when subjected to this incident radiation. The geometries that we looked at, or that I looked at, were elliptical clouds. So these are ones which go from being a sphere to being elongated along one axis. So you have a short axis in both X and Y and a long axis in Z, or some variation of length in Z. These are what are called prolate spheroids. And we also looked at them at different inclinations to the ionizing radiation. This causes quite a large parameter space. If you're just looking at spheres, you can look at like radiation regimes and things like that. Once you start including eccentricity and angle, you end up with quite a large parameter space. But we can start to look at what happens with these things. So this is an example of one of these clouds which starts off as an prolate spheroid on its side, so at 0 degrees to the incident radiation, and what's happened to it. And you can start to see some interesting features about this. Firstly, the two ends have much more compressed material, these higher column densities, and it forms a kind of surface structure on the top that's been flattened down. And I'm going to try, fingers crossed, to show a video. So hopefully this video shows. Excellent. There's no sound because as Alien informed us, in space no one can hear you scream, nor can you hear stars forming. So this is that cloud rotating in 3 dimensions, where these little blue circles indicate locations where we've got an extremely high peak of density. Now, these particular simulations, all of the masses that we used were comparatively small because it lets you run a more refined simulation. Your minimum simulation element is a smaller mass. But what we actually observe is that you're starting to get compression mostly at the two ends of the cloud. And I've got some videos of the angled clouds as well. And this is more or less what they look like while they're forming. So this is a low density cloud starting off as a prolate at an angle that's been subject to radiation from above. And you can see that you get this kind of wave cascading over the top of the cloud as these two edges come in. And the shock fronts are moving more or less normal to the ellipse. Now, when I go for a higher density, what happens is this. It doesn't look like that cascade happens. And that's because the simulation actually grinds to a halt. What happens is when you get extremely high densities in these simulations without using a thing called sync particles, what happens is the density has gotten so high that we can't make very large time steps. So this is creating a much higher density in this region than this lower density one, where you're getting the collision of the shock fronts, but it's not triggering a really high density. So what's basically going on here is that you've got two axial collapses. You've got, because the motion is perpendicular, normal to all of those surfaces, this flat upper surface is causing much more of a net downwards motion, and it's kind of pinching at the sides because you've got angles which are much more focused inwards. And what you're effectively ending up with at a variety of angles is that you get a sort of spine forming from this pinching effect, and these ends end up just clustering at the edges. So you get the two surfaces moving in, they're colliding at the point there. At a sufficiently high density, those points where they're hitting one another will get high enough densities that you might get a core forming. At small n, you'll basically get a turbulent region where these fronts have just moved through and past one another. You just get this mess left behind. And more or less, this can be depicted using a very simple kind of, this is an exceptionally simple model, but more or less, this is how much you expect the material to move in a given time just based on the flux at each point in the surface. And you can see how these lines converge at these two ends. The points in the middle that are flattish have a much larger flux per unit, much larger flux intensity per unit area. As you get to the sloped side, the actual radiation on it is a smaller amount and sideways, so they travel slower. And you get these bunching up at the end. And as you increase the angles of these, less happens down at the tail end and more happens at the sort of head of the structure, to the point where you're getting this sort of loopiness where it should pass through one another, until you're at 90 degrees, where you should basically get a proper focal point. I'll try and finish quickly because I think I've used up most of my time. So that's more or less the net behavior of these clouds as you go through these different angles. What was also noticed is that these turbulent regions can lead to really interesting shapes that actually in certain circumstances have what may be coincidental, but bear similarities to the kinds of structures we see in these actual regions. Those are these irregular clouds. This is mostly where you've created a turbulent region when the shock front has passed through another shock front, and you get these strange shapes. So these are different axial ratios. 2 is 2 times as long as it is wide, and these are different angles. And you mostly get these weird structures at high angles and longer ellipticities. And you get these weird, interesting shapes. And some of these look like some of the nebulae that you actually see that, well, not nebulae, the bright rim clouds that you actually see within some of these regions. That doesn't necessarily tell us anything because it's a visual sort of subjective depiction, but it does give us the ability to start to investigate these features more. I'll bring it to a close more or less there. One of the interesting things, this one here, ellipticity of 3 and angle of 60, looks an awful lot like a seahorse. And I felt confident that should it actually ever have formed, it would definitely have been named the Seahorse Nebula, or possibly just the Eagle Nebula as well, because I'm not sure how well that looks like an eagle either. That's basically all I was going to go through to try and keep it comparatively focused. Thank you very much for listening.
Great, thank you so much. I thank you again to all of our speakers that have joined us. Those were amazing talks, and we did go over by a little bit, but it was worth it for all these wonderful talks. So now until past, I'm going to take questions and I will pose them to the relevant academics. I have a couple written down from people that have submitted them in the chat, but feel free to keep putting them in the chat and let me know if it's not obvious which academic to pose it to. So I'm going to start with the question that I have for Dr. Bradu. So I had a question in the chat that said, are there any known techniques combining focused ultrasound to perturb the observed object and microscopy to monitor the changes in the object? Can't read my own handwriting.
Well, there are lots of techniques, using the well, based on photoacoustic or optoacoustics. Yes, and when you are looking for this photoacoustic signal, you can do it using different transducers, which are well, it's kind of microphones if you want. Yeah. So yes, the answer is yes. People are using all sorts of focused transducers or focused microphones if you want to pick up the signal. Some people don't use this geometry. Well, that depends in the end on the geometry used. That depends what you are looking at in the end. Yeah, right. Yeah. Well, we do look at biological tissues, and normally what's happening, we're only allowed to look at the object from one side. We don't go the other side simply because the object is too thick for us. In which case, it makes sense to use some focused transducers, but that depends on the application in the end. But yes, there are all sort of work. A lot of work is done on this area where focused transducers are used. Yeah.
Great, thank you. The next question I have is for Professor Burchell, which says, for rock ice impact targets, how do they determine the PAH to ice ratios? What kind of ices are being used besides H2O, and how are these objects stored?
Okay, well, there's a lot of questions in there, so thank you. First of all, I know it sounds odd, but inspired by Dr. Carr, you make toy models. You say, well, let's use water ice. We've also used ammonia-rich ice. We've used CO2 ices. So you think, which ices are out there? And let's start with simple ones. And some people take complicated ice mixes. So some of my colleagues here at Kent, Mark Price, and some of his PhD students and postdocs, for example, took a mixture of simple ices with nitrogen as well. And if you just hit them hard enough with a projectile, it turns out you make amino acids. So they found a way to generate amino acids on the type of ices, ammonia-rich ices, for example, you might find on comets or satellites of outer planets. So there's a lot you can do. Then what you do afterwards is you find a chemist, as has already been hinted, and you say, right, here's our ice. We've done something to it. Can you tell us what? And they very carefully measure it. And you have to look at before and after, make comparisons, and look at the yields you're getting in the laboratory. And this, again, is not real solar system. You're doing it on a slightly different size scale, but the speeds are about right. As I say, you can mix up your ice types. And then we just systematically vary things, trying to say, well, this could be what an icy body is made of. Let's hit it with a projectile and see what happens next. Then if we're looking at cratering or impact damage, yes, you've got to think of things like how thick is that ice shell around my icy satellite compared to the depth of water underneath it, compared to the radius of the core, and you try and scale things according to the models of how big these things are in the solar system. So you're guided by reality, then you think of it, then you do the experiment, then you ask a chemist what it is you've done. And so it's multidisciplinary work, like a lot of science today. And I specialize in doing the impacts. Some people specialize in synthesizing organic molecules. So the group working with Berkeley, they're doing experiments now. I don't even know what's in the ice mixtures anymore. They send us the ice mixtures with some amino acids in and say, see what the yield is when you try smashing these in your gun. So that probably tells you that I'm not the one writing those papers, but it is a field where you're guided by reality, inspired by simplicity, and you have lots of colleagues who supply their specialism while you supply yours.
Great, fabulous. So the next question was for Dr. Kinnear, and it says, can this simulation be reversed to take a nebula shape and figure out the angles and densities involved?
The answer would effectively be not really. The way some of these processes work you can't sort of treat them as reversible, because the end solutions are effectively degenerate. Multiple starting scenarios can give you something very similar at the end result. So there's no way to take if more than one route can give you the same result, there's no way to work out which of the two routes might have driven you there. But you can start to investigate what kinds of initial conditions, what regimes of initial conditions do result in those sorts of shapes. So you wouldn't be able to directly reverse a simulation, by conducting these parameter space studies, you can start to look at, if we start with these sorts of things, we get these sorts of structures or these sorts of statistical properties. So you can effectively do it that way by doing a larger survey and then working out what sort of initial conditions drives you to those given endpoints.
Thank you. The next question was for Dr. Ramos, and it was asking if you had any advice for moving abroad for your studies, your jobs, you know, moving around in this career path.
That's a good question. Rather complicated. So there are a few very practical things, like now that you can actually find out about a place using the internet, do find out about a place before you move there. Because, for example, you end up trying to find a place to live somewhere that you haven't visited, that you don't know very well. You want some information in case you end up in the wrong side of town, for example. But other than that, I think the main recommendation is go out with an open mind, because it's a wonderful experience to just move, try to learn a different culture, try to learn the language so that you integrate well and you can interact with all the different aspects of life that it offers you. So you get a lot out of the science and meeting people from different places, but you get a lot also from the fact that you're living somewhere else. And being prepared to just take it on and try to do the best to get a full experience out of it, it's life-changing. I don't know anybody that has moved abroad and has come back the same person that left. So very much worth doing, I would say.
Great, thank you. So the next question was for Dr. Carr, and that was, what is your favorite, this is quite a difficult question, what is your favorite piece of research you've worked on, or your favorite topic? As you've worked on quite a lot, and all of you have worked on quite a lot, so I guess it's quite a hard question to pinpoint your favorite, but maybe a top 3 or a top 5.
Yeah, that is a very difficult question because it changes every day. I think like the easy answer is my favorite is the one I'm working on at the moment. I do have some highlights throughout my career, I think. So if I go back and I look back on my papers that I've written so far, what are the ones that I think worked out best? And that's not necessarily it was my favorite topic, but just the contribution we made was quite nice. So, I mean, one of mine was calculating full counting statistics of something. So this is when electrons are traveling in an electronic circuit, you usually just measure the current, but actually you could measure the actual number of electrons as a function of time that have gone through the circuit. And then because this is quantum, there's a probability distribution of this. And I helped develop a way where we could do this numerically in a strongly correlated system. So this is, again, another example of where it's really useful to work with people with a different skill set, is that the numerical work is something I could never have done. However, some of the background analytical work that was needed to to efficiently do this numerically was something I was quite an expert in. So that was quite nice. And I mean, in particular, we found the one strongly correlated system where there is actually an exact solution, which we worked out for these things. That's very rare. There's some technique called integrability. Doing that out of equilibrium, there's even fewer things. And I think this is the only example where there's actually been a result which could be directly compared to numerics quite successfully. So that was quite pleasure to work on.
Okay.
I mean, other things I think just depend on who you're working with at the time as well, that you make really good friends with different collaborators.
Yeah. And we have another question for Professor Burchell, which says, when scaling up from a 1 to 2 kilo collision to planet-sized, how do you account for the gravitational forces, and are there ways in the study of craters to verify your extrapolation?
Well, the world is divided between those who do experiments and get all the physics right because nature supplies the physics, just doing it at the wrong size scale, and those who are modelers who are at the right size scale with their models, but they have to put the physics in. And did they put it all in, and did they put it all in right? So somewhere in between, we try and talk to each other, but there is a problem because yes, what would be nice would be to observe in real time a very large impact where we could see the impactor, know what it was hitting. And this has sort of happened with Comet Schumacher-Levy 9 back in about 1993, I think it was, when it flew into the atmosphere of Jupiter. But in the main, we do have a problem. If it's an extrapolation, we do it in the lab at a strength regime where the material properties are all dominated by material strength. If you go to larger scales, gravity does play a role. And so you have to introduce gravity in your extrapolation. So suddenly you're now extrapolating into a regime with some basically different physics. And if you're doing a model, you can put all that in. But the modelers, well, one of the things they do is they run all their simulations without any internal strength because the shock pressures are so great, strength's irrelevant. Then about 80% of the way through the simulation, they say, oh, we'll turn the strength back on now. Why is that right? Well, because the answers look right. We end up with craters that look like craters that are real. Got the same shape, same depth to diameter ratio, same sort of height. So I was at a talk where a very famous modeler was being given a prize. And when he actually said this part of the way through his speech, oh, we just turn the strength off and then turn it back on after about 80% of the time because that gives the right answer. There was actually gasp from the audience. You can see them think, what, we've just given this man a prize? But it's because that's where you have to have scientific insight and exercise judgment. And if everyone agrees you're getting it right, and there's enough corollary evidence to say that, yes, the craters now look right coming out your models, or that the things you've predicted in the laboratory, for example, I can predict what's the maximum size crater you'll get on a body before the body breaks apart. And if that comes out about right when you extrapolate it to solar system scales, in other words, you've got to now photograph things around the solar system and look for the largest crater on a small body, and it's the same ratio as in your lab extrapolated upwards, then people start saying, okay, you seem to know what you're doing. But it is odd that we like to think of ourselves as, hey, we're great scientists, we control everything, we know everything. And the reality is we don't control everything and we don't know everything. So we make a suitable approximation and then go and see if we can find evidence to support it.
Thank you. So I'm now going to pose an open question to all of you, and I'll call on you to give your answer. We've had someone ask, what is your favorite thing about being a physicist? So I'll come to you first, Dr. Browder.
Right. Well, the thing is that I like the fact that during my career, let's say, I was able to do different things. And well, I could do research, and perhaps that's the reason for which maybe I moved to England. You know, because I moved from a country in France where, you know, doing research, well, you can do good research there, but you are not really, you know, if you want, allowed to do it for a long period of time on your own. So, because you have this period when you do a postdoc, that's the greatest period in your career, perhaps, for doing research. Now, well, my advice to everybody as well is to do not one, but 2 or 3 postdocs if you can. Yeah. And I think most of us actually did this in the past, and perhaps we enjoyed all that period of time. And then you go and you teach, yeah, and you teach what you have learned during those years of postdocs. I think this is absolutely great, yeah. So that's my view on this. Okay.
Fabulous. Dr. Ramos?
I think it's difficult to say one thing. I like the fact that it's never boring and you learn something every day. I mean, when I was a kid, that would have been the dream. You go out there and you do a job where you learn something every day. And I think that's wonderful. But something else that I didn't know at the time, but it's become a definite plus, is the people. You meet lovely people, really interesting people that know really interesting things with quite incredible sense of humor half of the time. It's really lovely. So it's both sides. The fact that you're really never bored and you always learn something, and the people you interact with, which tend to be really lovely.
Great, thank you. Dr. Kinnear?
I think it's quite, I'd agree, it's quite difficult to pin down. I certainly think that Dr. Ramos's comment to do with there's always something basically novel to look at. There are certainly elements that are routine in terms of what you do, but you know that you're directly connected to something that is beyond that, genuinely completely new. I really enjoy the teaching element of it all. Whether the students do as much as I do, I don't know, but fingers crossed that's the case. Yeah, I think the actual novelty and also a very large degree of ability to effectively, well, to a certain degree, maybe less so currently, manage your own time in terms of how you go about doing your work. It's not super prescribed and you can work to the sort of best of your ability. I think that's more generally working in science rather than physics specifically, but yeah.
Great, thank you. Dr. Carr.
Yeah, I'm going to borrow a book title from Feynman to answer this, just say the pleasure of finding things out. And be that in research, where when you've finally worked out something, you realize you're actually the only person in the world who knows it at that moment, mostly because no one's ever thought of that before. I mean, if other people had thought about doing it, they would know it as well. But it's a pretty cool moment. And also, I mean, the first time you give a lecture course and you prepare it and you realize actually you knew nothing about this topic and now you actually finally learn it. And then when you're giving lectures and students ask interesting questions, I'm afraid I've got a cat joining us. And the students ask interesting questions which make you think deeper about the subject and think that's a topic I've never thought about. And I mean, just generally that there's always stuff to learn. I mean, being an academic, I think, is the same as being a student forever, which is pretty cool if you enjoy being a student.
Going to be a forever student. Yeah, definitely. Thank you. And lastly, Professor Butcher.
Well, community, but Dr. Ramos has already said that, and it is a welcoming community that you can go around the world to different physics laboratories and you're instantly in the front door. Because physicists welcome physicists. I'm sure other subjects do as well, but physicists are very good at it because we are networked and we work on large collaborations frequently. We welcome each other into labs and share, so that's very good. The discovery has already been mentioned. The fact that someone's paying you to go out and discover stuff. This is wonderful. So there's a joy. That teaching has also been mentioned. That I would say about half of the students are there. In fact, all physics students do physics because they want to. Half of them really want to do physics and really, really want to do physics. And yes, and the other half want to get good jobs afterwards. So that's fine. Both destinations are valid. And then it is just this, I wanted to travel when I was a teenager. I grew up in Southeast London, living in council houses, wherever. How was ever I going to go to Switzerland? Which I did, lived there, right, yes, sir. How was it going to end up in California? I lived there for 3 years. So there are these opportunities. I'm sure other careers give them as well, but physics gave me so many opportunities to meet people, to do the things I wanted, live in wonderful place, and now living in Canterbury, which has already been mentioned is a very nice place to live. You've got some control over what you do every day, right? You've got to give that lecture now, 9 o'clock, you've got to be there, just like the students. But it is fun, we can enjoy ourselves, and we do welcome people as a community. So I think all of that put together was a perfect package for my sort of life.
Yeah, I would agree. It sounds like a great career path, and I'm excited to be a part of it. So yes, that wraps up the Speed Science event. Thank you all again for joining us for this hour and a half. This has been great. Professor Mason is endorsing all of your answers there in the chat, so that's great. Yeah, so we're going to take a half-an-hour break now, and then at 7 p.m, Anthony is going to be back hosting Are You Smarter Than an Undergrad? So you can watch Anthony host this quiz-style show where he's going to be quizzing professors and doctors on their undergraduate degree knowledge. So it's found to be interesting, and I recommend you come back for that. But for now, we're going to have a half-an-hour break. So thank you again to our wonderful speakers. Thank you all for joining, and I will see you in half an hour.
Thank you, Molly.
Thank you.
Thank you, Molly.
Bye-bye.
Thank you, folks.